very high. But I mean, that's the purpose. You guys started really hard. I think you deserve it. But looking over exam two will be a little bit more harder than the first one, and the last one, of course, is the hardest. Yeah, go ahead.
The exams are not cumulative. The midterms are not cumulative.
No, this semester we tried. It's not cumulative, but when you get to the final, it uses a lot of information from the previous chapters.
The components that we used here will be included in the final.
Exactly. The components that are from the chapters will be carried over to the final, which if you missed the couple chapters beginning, and you will not be able to do the problems because they carry the equations, carry the symbols and the tools.
It just won't include stuff like
we don't have
the first one was just basic. So first chapter was review of basic.
Right.
Circuits 1 and 6.
It's mostly 5 and 6 are carried over to 7. Okay, so mostly. So second one doesn't have a lot to do with the previous chapters, op amps, but yeah, there will be a little bit of using op amps. Some circuits might have a diode, things like that. But we don't have a dedicated problem to ask you about diodes, operations, things like that. Okay. Yeah, so let's get ahead. So this class actually gets more difficult at this point. So, look at op amps. The reason you guys do well, because I think many of you have done pretty well in 210. So that was kind of a review a little bit. But the problems are not harder than the problem in 210. So that's why. And diodes, of course, very simple. There are only 3 operation modes. You look at either ideal mode or constant voltage mode, or there's a spice mode, or things like that. But once we get to chapter 5 and chapter 6, it does get harder because there are a lot of mathematics involved. So instead of focusing on the kind of physics or linear characteristic like diodes, now we're getting nonlinear. There's no way to linearize MOSFETs and BJTs. Now we do that in like power electronics class, 584. We linearize them. We say, okay, either on or off. But in this class, all focus is on the small signal. So all focus is on like very little voltage, very little current, but they always operate in a region where it's nonlinear. So what are we going to do? Actually, a few announcements actually. Professor Ashrafi told me that some of our students come into the class too early, so interrupt his class. His class finished at 9:15, so don't get into the classroom before 9:15. Okay, so just for courtesy of other people. Another announcement is that for the next 2 weeks, so starting Tuesday next week, our class will be fully online. Okay, for 2 weeks. So you guys don't come here, but I will also send out announcements via.
Online is in Zoom.
Or
like
yeah,
video instruction.
It's most likely I'm going to record them ahead of time, just because I don't want to get to the point where I don't have internet and you guys, everybody sitting here waiting for me. But I'll be online, so you guys, have questions. So and those videos will be released at the time of the class time, so you don't have to worry about taking early ordination. Yeah, so every video will be released at the time. So so don't come to classroom during that time. I mean, there's nothing wrong to sit here, but of course, it's better to just watch it online. Okay. Yeah. So I think that's pretty much it. So let's move on. So in this chapter, we focus on MOSFETs. So MOSFET stands for metal oxide silicon. So metal oxide silicon MOS. FETs mean field effect transistor. Silicon. Well, the different ways. Yeah, you can. Yeah. And then FET means field effect transistor. So transistor, you see how transistor gets a name because we have diodes. Diodes means you have p-n junction. And you have transistor that has 3 terminals, so tri. So that's probably where I am, but I don't know how they got this name, but it has 3 terminals, okay? So it has a controller terminal. So we are going to, in this today, we're going to go over the device structure and physical operation, which is section 1 of the book. And then starting next lecture, we're going to go to current voltage characteristics. Okay, we're going to spend 4 lectures on that. We're going to go through every single example and exercise in the book. So just get you guys again, just repeat. So hopefully, my hope is that by the end of the chapter, oh my God, it's written in my brain. Okay, so that's how we're going to do this chapter. And then of course DC analysis and so on. And then finally, just about half lecture on the future technologies about MOSFETs. Yeah, so sometimes they say metal oxide silicon, but sometimes they metal oxide semiconductor. So this word can be switched between silicon and semiconductor. And here we have the most important word is the field effect. So we're going to explain what they mean in that MOSFET. So this is a physical structure of a MOSFET, but this is nowadays this is in a nanometer scale. So it's like in the old days, of course, it was big in the micrometers. In the beginning, it was in the millimeter scale. But this is in large picture. What we're doing is we first build a substrate. This substrate is also semiconductor devices. So it's a P-type. You guys know by this time what P-type means. P means it has a lot of positive ions in the free holes inside the semiconductor device material. And then on this substrate, we dig 2 like wells. Like here, you see, this is this way, right? So you dig this way, and you dig this way, and then you put N-type material. N means a lot of electrons, so it's a negative material. And this is N plus. N plus means it's more than the regular N-type material. The regular N-type material might have 10 to the, say, don't quote me wrong, I have to look at it maybe. So let's just assume 10 to the 17 electrons. But the N plus means it may be 10 to the 19. So it, like 1 or 2 order higher number of electrons inside the material. So you put here. But you know, silicons don't conduct. So in order to conduct electricity, we have to put some metal to collect the current, right? So you cannot solder like something directly onto. So we put a metal piece. So this is a metal piece. This is called, and then in the future, this piece is called body. So the P substrate is the body. Without the body, you cannot make the semiconductor. So you have to have a body to hold the MOSFET. So in the body, we dig 2 wells and we dope N-type material, the N plus material. And then on the top surface, on the N-type material here, we put a metal. And on this here, we also put a metal. But between these 2 N-type material, there's a little bit distance. So within this distance, we put a silicon. This is a purely like a layer of silicon, like an insulator. It's not conducting, it's not semiconductor, it's purely silicon. And then on top of this silicon, we put a piece of metal. So you can imagine that between this metal and this body, there's not going to be any current because there's insulator in between. So it's a silicon, it's insulator. So there's actually no current flowing between the metal and here. So now you have metal oxide. So you have metal connected on all the pieces, but especially in this area, we define this as a gate. Okay, you will see why it's called gate. So the gate is a metal. So you connect that. This is a flat piece, like capacitor type of piece of metal. And then below here, you put a silicon oxide. So this is, I was wrong talking about silicon. So it's a silicon oxide. So it doesn't conduct. So this is like an insulating between gate and the body. So that's why it's called metal oxide and then silicon. So so that's why the student asking whether you call it metal oxide silicon. So that's kind of the structure of this MOSFET. So for this MOSFET structure to work, basically, we are looking at so if you look at the structure on this cross section, you can see that there's a N-type material, there's a P-type material. So over here, you form a NP or PN junction between body and between the substrate and the well. And then another one also from another PN junction. Okay, and then so there's like a PN junction here, there's a PN junction here. So for this to work, what we're going to do is we're going to apply a voltage at the gate, see what happens, between gate and body, and see what happens. Here we have just clarify some of the terminologies. Here, this side is called drain, the other is called source. But if you look at the structure, it's actually symmetrical. So in real life, these two can be swapped. So this can be drain, this can be source, it doesn't matter. And then the other definition is here, is metal is connected to gate. And between gate and this channel, later on we're going to talk why it's called a channel. And this is oxide thickness, we call TOX, so it's a silicon oxide. And if we read from drain to source, you see there's N, and there's a P, there's an N. So this is called NPN type of MOSFET, or sometimes called N-type MOSFET. So it's drain is connected to N, source is connected to N, and then in the middle, it's the region is called a body. So what happens is we apply a voltage at the gate. All right. So what we're doing now is we're going to apply a voltage between gate and the body. Now, when you apply a voltage between gate and body, you see here at the body, there's a piece of metal as well. So between two metal, you apply voltage, what happens? No, there's insulator, so there's no current. So there's a voltage across these two metal plates. Well, what do you call them? It's like a capacitor, right? So there's an electrical field in between these two metals. So there's an electrical field. So there's an electrical field going this way, basically. There's E field. So when you have a E field, imagine that you have a E field, which this side is positive and this is a negative, right? So when this side is positive, it's over here. So there's positive, right? And then there's negative here. That's the voltage source, right? So imagine what happens between there's a positive charge at the metal plate because there's a voltage applied, no negative. All the electrons inside this P substrate is going to be attracted. Now, the electrons in the N plus and my material, they won't go very much because there's a barrier, there's a PN junction, so they're not going to jump. There's going to be diffusion area between the PN junction, but the electrons inside this P substrate material, it's going to move. Where are they going to move? They're going to move here. A lot of move, right? The positive ones are going to move here. So that's going to balance, right? So you got negative electrons move this area. So once they move here, they accumulate like in this small region between this surface and here. So there's like a channel of electrons keep accumulated in this area. Okay, so this one shows in the lower graph, it shows like this. So in this area, a lot of electrons. So that's what happened in the big. So this phenomena is called field effect. So when you apply a field, the electrons are going to accumulate at the surface. And then, okay, so this same thing. Well, we said that the path between drain and the gate, between drain and source has a very high resistance in the order of 10 to 12. So if you even apply a voltage over here, like previous one, like if we apply a voltage over here, no current, because the resistance is too high. The channel, like right now, it's no resistance. But what happens is something is going to change is we apply a voltage over here. Remember what I said before, when you apply voltage here, all the electrons is going to form this channel. So all the electrons are here. So now you see what happens. When you apply a positive voltage on here, now it's like it's like a wire connecting this end and that end. So this the electrons are going to come out of the negative terminal. It's going to come here. It flows all the way to the other end, and it's going to go back to the source. So it started to flow current. So this is called a channel effect, and then the current started to flow. So this is a very, very interesting and a very simple phenomena. Is that, well, okay, so right now, this is like for the illustration, it's better than my hand drawing. So what it says here, if you apply a voltage to the gate, you can see that all this region is going to become filled up with electrons, all the electrons. And between these two, between this end and this end, we call the channel length. Why? Because this is like a channel, and electrons go from here to here. It takes some time, so that's called channel length. If you look at like that way, like if I'm looking this like in this direction, it will be like this big, right? So this is called width. Okay, so and you can imagine that the resistance of this channel is proportional to what? Length, right? But it's inversely proportional to the width, right? So I mean, I got it wrong. So the resistance, yeah, the resistance is proportional to length by width. And then, in other words, the current is going to inversely proportional to L, which means the longer it takes, more effort for electrons to flow. So L is inversely proportional to current, but this width, like this direction here, you look at this direction here, that's going to be proportional to the current. So the larger area, more current can flow.
So when the electrons bunch up around both N pluses, like it allows current to flow from S to D?
Well, depending on which you apply voltage, we normally flow current from D to S.
Oh, but
yeah,
that's like the main channel we're stuck.
The main channel, yeah.
G and B is just like applying a voltage, right?
Right.
Okay.
So here, like when we started to connect the current, connect the voltage at the gate, now the channel is full. And when I apply the voltage source at the drain, see current start to flow. Okay, so it's continuously flowing through the channel. So the bigger the channel, the more current. So how do you make this one? The length, the shorter the length, the more current, and the bigger the channel, the length. All in this, this horizontal direction, in this like depth direction, the bigger, more current. So that's how these things work. It's very easy to calculate the current. There's a couple of parameters, like mu and COX is a property of the silicon. Like what type of silicon, how much electrons, things like those are the properties that when you dope the silicon materials or semiconductor material. So those are given, basically. And then we have, I just said earlier, that WOL is proportional to current, right? So when more W is more current, less L is more current. And then there's also a term called VOV. So a couple of definitions. Now imagine that this VGS, this VGS has to be large enough so that this channel is forming. If you apply the voltage too small, yeah, some electrons are going to move to the channel, but it's not enough to form this continuous flow. Therefore, you will not have current. So that voltage is called threshold voltage, VTS. VT, I will call VT. So VGS how do you get it over this? So VGS has to be larger than VT. VT is called threshold voltage to conduct current. And secondly, VDS has to be large enough. Because even though there's a channel, but if VDS is not strong enough, it's not going to move the electrons, right? So VDS has to be large enough. How large? It has to be larger than VGS minus VT. So VGS has to be larger than VT, then VDS has to be larger than VGS minus VT, and VGS minus VT is called VOV, it's called overdrive voltage.
Oh,
VGS is the voltage between gate and source. Yeah. So when you satisfy these three conditions, we can write the current. We can write the current of the inner device, but that current is going to well, actually, this is wrong. So what we call it is in saturation mode. If VDS is less than VGS minus VT, it's going to be triode mode. So the difference is that in the saturation mode, you have more current. In the triode mode, you have less current. So I just said earlier, maybe it was not accurate. So VDS has to be large enough so that you will have some amount of current. That VDS is related to the amount of current flowing. So of course, we're going to come back to all these equations more and more. So here, when this is they call it a linear region, which means if your VGS is kind of VDS is very small in the linear region, VDS is very, very small. How small? Like 0. some volts, okay? So when VDS is small, when VGS increases, you see, when VDS 0, there's of course current 0, regardless of VGS. When VGS increases, at this point, VGS is same as over threshold voltage, there's no current. But then when VGS start to increase, and then you have VDS, you have start to have current. So these are the linear region. We don't really care about the linear region because that's the region we don't use it. So here we have an example talking about this different calculating different parameters. So this is the solution given. So I'm just going to give you some like a process. So what it says is a 0.18 micrometer fabrication process. So what does that say? So which means the length is a multiple of 0.18 micrometers. L is multiple. It can be 1 block or 2 block. It's like a building block. Okay, it's 1 point. It's like you make this slice, and then you make another slice or a third slice. And it says mu, 2x is the thickness between the metal gate and the P substrate, right? So the silicon oxide thickness is 2x. And so mu n is 450, that's another parameter, and VT threshold is 0.5. So they ask you to find the value of W width so that the device exhibits a channel resistance of RDS 1 kilo ohms and VGS is 1 volt, at VGS 1 volt. So what you're doing is, first of all, you need to calculate, we need to calculate like COX value, which epsilon OX is a permittivity divided by TOX is a thickness of the silicon oxide. Then you get this, plug in the numbers, you get 8.6. This is F farads per micrometer squared. So this gives you a number, right? And mu n is already given. So mu n is given 450. So we can then calculate this number. This number is called Kn prime, is mu n times COX. Of course, you can get some value. And then VOV is also given. So VOV is given, no, VOV did not given, VT is given. VT is given at 0.5. So our VGS has to be larger than VT in order to conduct current. And VGS is given at 1 volt. So and VGS is given at 1 volt. So it is larger than VT. So therefore, it's going to conduct current. Right? So our VOV is VGS minus VT. That's 1 minus 0.5. That gives you 0.5 volts. And our GDS can be calculated. And in the book, it gives you equation. So Kn from W divided by L times VOV. Now, this equation is calculating the resistance between drain and source. And remember, the device structure is like this. So this N plus. So this is the channel. So this is really looking at the resistance between. So this is GDS, this is the RDS is equal to 1 over GDS. So GDS is the conductance, RDS is resistance. So because I mentioned earlier, so the resistance between this one and this one is inversely proportional to the length. And proportional to, the resistance is proportional to the length, and inversely proportional to the weight. So that's why you have resistance here. So yeah, so if we write the resistance, it's going to be reverse of this one. So it's proportional to L and inversely proportional to W, and it's proportional to some sort of silicon parameters. So that's silicon oxide parameters. That's this one here. So VOV is overdrive voltage. It's VOV is VGS minus VT.
But you say here that VGS has to be greater than VT, but in the earlier example, you said that VDS has to be greater.
No, VDS has to be larger than VOV. VGS, in order to be in saturation. So for the MOSFET to conduct, VGS has to be larger than VT. The difference is called VOV. Yeah.
What about the VDS has to be greater?
VDS, later on, we'll talk about it. So VDS can be from 0 to whatever volume. But if VDS is too small, it's in the triode region. Like diode, now it's a triode. And if VDS is big enough, it goes to saturation region. That's the region that we want to use. So
How do you calculate VOV again? Sorry.
VOV is VGS minus VT. Yeah. So in real life, what happens is that when current started to flow, the electrons coming from the negative terminal, because current direction is opposite to electrons, right? The flowing direction, right? So electrons coming out this way, and it comes this way. So a lot of electrons coming this way, but everybody like try to squeeze into the channel to go the other way. So naturally, you will see more people over here, less people over here. It's just like, all the people come out of something, everybody try to get into a hallway. A lot of people coming into the hallway, doorway, right? But because so many people are squeezed here, so if you look at the other end of the hallway, it was not so many people because everybody tried to squeeze in. So more electrons here, electron here. Now you guys look at this. What happens to the resistance if the channel becomes like slanted? the resistance going to increase, right? So more resistance because this side is much, but less current can squeeze in. So the effective, like this thickness becomes less. So that's why this is called a channel effect. So a channel effect means the channel becomes not straight anymore. It becomes slanted. One side is thicker, one side is less thicker. Okay. So the current, due to the channel effect, is replaced by here. So they called. We're going to introduce a few equations here now. So the first equation in the linear region, again, the linear region, it's ID equal to there's a mu n COX is a property of the silicon. So that's kind of natural property. And then W is a width, L is a length, and then multiply VGS minus VT, that's the overdrive voltage. And then multiply with VDS is the voltage between drain and source. That gives you a current. That's in the ideal situation. Okay, so this is the ideal situation. But then the problem is that when the channel length started to change, like this overdrive voltage here change, and all the way come to here, you got less. So therefore, the effective area is no longer VOV times like WOL, but actually it's going to be this. It's going to be the like this trapezoidal form. You look at the total area and divide by this length. That gives you the total area. So this is why we have VOV minus 1/2 VDS. So this side is VOV minus VDS. This is VOV. The channel effect is reduced by VOV minus VDS. So instead of VOV this much, and use VOV minus VDS and gives you this much. So therefore, you take this two and take an average, like take the average thickness in the middle. That's what you do. VOV minus 1/2 VDS instead of VDS. So we got this. VOV minus 1/2 VDS times the VDS. So this is the current. This equation is very important, but you guys don't have to memorize this. You can write it down, okay? But we will coming back to this equation again, again. And we're going to introduce other equations too at some point. So when this thing, MOSFET is when, so earlier you asked what happened to VDS? Well, this is what happens when you give a bigger picture. When VGS is larger than VOV, the VGS larger than VOV by VT, okay? So this, you can say, so VOV is VGS minus VT, right? So VGS is VT plus VOV. So this equation is naturally a variation. So when this is true, when you increase VDS, initially it's in the linear region. So this region, this small region is linear. Even though it doesn't look really like linear, but over here maybe a small region is linear. So current increase quite fast. But then it goes slower and slower and slower. And all the way it gets to some point, like here. When VDS is equal to saturation voltage, this voltage equal to VOV, the current becomes flat. So if your VDS reaches this point, regardless how much VDS you increase, the current does not change anymore. It's a constant current. So this is the property actually we are most interested, because we can apply whatever voltage we want, and the current will be essentially the same. But of course, this phenomenon, later on we're going to talk about, it's not exactly flat. It's still actually a little bit up, going up, but not as much as here. Like here, you go to very fast. And this region we call trial. And this region we call saturation. In the trial region and the saturation region, the two equations are very different. Now, the equation already given in here, but I want to write again here. So in the trial region, you have ID equal to K n prime WOL times VGS minus VT times VDS minus 1/2. That's in this region, But in this region, you got ID equal to 1/2 Kn WOL. Kn, there's a prime signal, and times, oops. So as you can see here, the first equation has something to do with VDS. So there's a VDS in the first term, there's another VDS, which is this equation here, this in tried region. This VOV is VGS minus VT, so you can replace that. So this is the voltage for the tried region. But for the saturation region, VDS is all gone. So it's all like constant. It only has something to do with VOV or VGS minus VT. So these are the two regions that that we work on them very frequently. So when VDS is larger than VOV, yeah, we talk about this, but this is the equation that I wrote earlier. This is the equation, but also you can replace this one with this and with VOV. So those two equations, again, well, you guys don't have to memorize, but you need to write it down. So I'm going to do some examples because I know this is quite a lot, right? So this equation here, equation there, which equation to use, things like that. We're going to, again, go through a lot of examples to make sure you guys catch everything. But before that, let me also get you guys to know PMOS. So the early one is the NMOS. I mentioned it's N, PN, because the middle one is the big base is the P substrate, and you got two N wells, right? N, PN. But if you want to make P-type MOSFET, you will do the same thing. So instead of P, now you have N-type substrate. So this is N-type, and then on N-type, you dig two wells, you dope material to make a P+. P+ means it's a lot of holes, but it's more than the regular silicon, so it's a plus. And you make two of them. Similarly, you make a metal and you make a silicon oxide between metal, between gate and here. And here, substrate also, you have a metal connect to, usually this is connect to ground. And a lot of applications, the body is connected to source. So basically, or in this case, connect to drain. So when you apply voltage at the gate, you see what happens this voltage. Instead, positive will apply a negative voltage. Okay, so now you form a channel, but this channel is called a P channel. So when you have like negative voltage here, positive voltage here, so the holes are going to be attracted to here to balance the electrons on the metal. So this forms a P channel. When you form a P channel, you apply a voltage at the drain, or you apply voltage at source negative, but here you apply negative voltage. You see electrons are going to move from here to here. I mean, not electron, holes are going to move. So therefore, the holes move this way to combine at the negative terminal, you have a current. So that current, again, is also called a channel. So we call this a PMOS, or P-type MOSFET, PMOS. And PMOS and NMOS, they are just opposite. We do when we do examples and homeworks, and probably in your exams, we're going to have both PMOS and NMOS. And again, we're going to talk a lot more through examples and exercises to get to know them. And in the latest technology, we actually built NMOS and PMOS on the same body. So when you build this, they are called complementary MOSFETs. So there's a NMOS, there's PMOS. the way that they build this is first they form a p-type body. In the t-type body, we dig two wells and dope them to N+ material. And then so when you dope this two, you can see that this forms an NMOS. But on this NMOS, on this p-type substrate, we dig a big well. Then this becomes the body of a PMOS. And on this body, you dip two wells and you dope material to make p-type of semiconductor, and then this forms PAP. So avoid this kind of short circuits, we put a silicon oxide between NMOS and PMOS. So this you can see here. You build this one here and this one here and then that one. So there's a silicon oxide to prevent the MOSFETs, between the MOSFETs, prevent any current to go through. So this is called a CMOS, complementary MOS. This is very popular in many applications, very popular. So now let's go through example. Yeah. So basically, in this example, what was given is it says the technology is 0.18 micrometer. So what really says that, so this MOSFET is built this with like building blocks. So the length is a multiple of 0.18. So it can be one slice or two slices, three slices, four slices, like if you put a slice together. And then TOX is the thickness is 4 nanometers between gate and the body. And then mu n is given 450 and Vt is 0.5. So first of all, they want to find COX. So COX, you know, if you do on COX is basically is this one divided by 2x. So that's what was given. And then if you want to find the k, k prime is COX times mu. So those are numbers that you can easily find for the device. So okay, so the second step goes as okay, if W over L is 1.8 over 0.18. So W is the width of the MOSFET, and 0.18 is the length. So if WL is given, we want to calculate the values of VOV, VGS, VDS mean to operate transistor in the saturation region with a current of ID is equal to 100 microamps. So to do that, we need to find out what is the relation of current. Previously, we told you that if it's in saturation region, ID is equal to 1/2 K prime W over L VOV squared. So that's the equation from here. You can find VOV is equal to 2 times ID over Kn prime W over L square root of that. So you take the square root of that, you find VOV. So this is a fairly straightforward calculation for given equation. But the most important thing that you follow like how to get that and then find this one. Especially it says saturation, we use this equation. If it says in trial, that's a different equation to use. So in trial, we use this one, we get VOV. So the value, the solution on the next page, let's see how much VOV, so 0.23.
How would you get that without knowing I?
How what?
Without knowing ID. What's the thing on the top?
ID is given 100 micrograms.
Oh, yeah.
ID is given 100 micrograms. So you get VOV, right? So VT is given, right? So we know that VGS equal to VT plus VOV. So that's 0.7. So VGS given. And then, of course, what is the minimum to open the stuff in saturation? And we know that VDS has to be larger than VOV. So VDS has to be larger than 0.73 volts.
So what would be the minimum?
Hmm?
What would be the minimum?
The minimum will be VOV, yeah? So it's going to be, yeah, equal as well, yeah, 0.3. But of course, at that point, the current is 0. That's exactly the start point. So the current is still, yeah. I'm sorry. The current is not 0. This is saturation mode. It's a start point of the current to go to this flat point. Yeah. So this current is like this.
It's like the very first time the current is
saturated. Every time it's in the beginning that at this point it's saturated. Yeah. So and then the next one says, okay, find for the device in B, find the value of VOV and VGS required to cause the device to operate as 1,000 ohm resistor for very small VDS. Now you understand what it means, right? Very small VDS means VDS is going to be smaller than VOV, so it's going to be in the triode region. So if it's in the triode region, we have to copy the equation. Even I don't remember all the equations. So this RDS over here. So RDS equal to, oops. So RDS equal to, let's write down, oops. So this is your equation, right? So now RDS given is 1,000. So Kn prime is given, WOL is given. So now you can find VOV. So VOV basically equals 1 over Kn prime WOL RDS. So that gives you your VOV. Oops. And then once you find a VOV, because you can find a VDS. So VDS is difficult. It's a little bit difficult to find because what happens is that this is in triode mode, right? So in the triode mode, or VGS, not VDS. So VGS is going to be VOV plus VT. So that's the equation we find. This is the equation we find VOV. A couple of things. I think I'm not going to go too much. Maybe to the next time I'm going to go there. But what I'm going to come back is that to mention a few things here. So if a MOSFET has this what we call it Kn prime, and this Kn prime, if we take that, we also have Kn equal to Kn prime WOL. So they just in the book, I mean, in actually all books, they do this. So from Kn, so in the future, you guys say, okay, there's a Kn, but there's going to be Kn times, oh, look, really ugly. So it's going
to simplify how you write equations.
Yeah, it's going to simplify sometimes to write equations. So if you do this, your current in the saturation region becomes ID equal to 1/2 K times VOV squared. So all it does is just simplify the equation, right? So then this is for NMOS. Now for PMOS, what happens is that it's going to be for the PMOS, the VT it's called VTP actually. So we use like this, use absolute value. So and VOV is going to be VDS minus VTP, this absolute value, so we use this absolute value for PMOS. This is how we're going to express those PMOS, but then the current is going to be similar. So the current in saturation, you have ID equal to 1/2 Kp. So that's for the PMOS. And for triode mode, it's going to be also this. The equation is very similar. Oh, actually, we in the future we don't call it VGS, we call it VSG. So now I write it here. So in here, I'm also gonna write the triode region. In the triode region, for the MOS, I want to write it here, guys, to compare this to VOV VDS minus 1/2 VDS squared. Okay, so these are the two equations. In the future, you have PMOS. We're going to use this mode, and MOS. We're going to have so this MOS, this PMOS. So these are the symbols in the future we're going to use. So for MOS, current flows from drain to source. So current flows here from drain to source. And for PMOS, current flows from source to drain. You could look at this little arrow that's pointing the current direction. This is the current direction. And because the gate is insulated, so there's no current from gate to the body, no current here. So the gate is no current. Therefore, that's why this shows, that's the reason MOSFET has this like a little gap between gate and the body, because there's no current. And this is just very interesting representation, there's no current. So the conclusion that if there's no current from gate to the body, you can say that the drain current and source current are identical. So this current is always identical. And here too, are identical. So when we say IS, it's always same as ID. Always ID is always same as IS. So in order to avoid any like confusions, I'll say we always use ID. So here we said ID goes here to IS. Same thing. So here you could have said IS, but we also say ID because ID, IS are same anyway. Right? So we say ID. So in both cases, we say ID. And the two operation modes, again, when VGS, okay, so here for MOS, if you look at the directional current, so the voltage at the gate has to be higher than voltage S in order to have current. Not just higher, but it has to be higher than VTN in this case. So VGS has to be higher. So the potential between gate and source has to be high enough in order to have current. So that's why you can VGS larger than VT in this case. We're gonna have tables in the future to summarize during almost every lecture. But for PMOS, if you look at the directional current, it goes from top to bottom. So if your gate voltage is higher than S, it's not gonna have current. So that's why we need to have current, we need to have voltage at the source higher than G. So voltage source has to be higher than G in order to have current, to flow this way. So that's why we call it VSG. So going back to this equation here, we say VSG minus VTP. So it's not VGS, but VSG for PMOS. But for other one is VGS is VOE is VGS minus VT. Okay, and then the other thing is that look at here, because the current flows from the drain to source, so there's a voltage drop across the transistor between drain and the source. So we call this VDS. But in this case, current flows from source to drain. So therefore, we have voltage, we call VSD is positive. VS has to be larger than VD. So VSD. So there are a lot of similarities, but there are also a lot of differences. But when you do PMOS, there's one thing, of course, we're going to have examples in the future. If you memorize that VSD, if you use everything absolute value for PMOS, it's going to be identical as NMOS. So one of the questions you're asking often is that, if that's the case, why would you need PMOS? It is a little bit difficult to say, but sometimes, for example, in this case, we can apply a positive voltage here, but we can ground this. So we can ground our gate, but this will still have current. But in this case, you cannot ground your gate, but you have, if this, unless this is a negative voltage, otherwise you cannot ground this one. But if this is a ground, this has to be higher. So gate voltage has always some value, right? So the different applications where you might need PMOS or NMOS. And also what happens when we have NMOS and PMOS together, when we design like logical circuits, all the different gates like AND gates, NOR gates, things like that, you're going to use a lot of this PMOS and NMOS configurations together, called it CMOS. Another thing I want to remind you that because the MOSFET is symmetrical, so the source and drain actually are reversible. So you basically, even though we have a current like this direction, you actually can reverse this one, use this as a drain, this as a source, current will flow this direction. There's nothing wrong with it. So MOSFET is always like that. But what happens is that in the future applications, you actually see this. And in PMOS, you actually will see you say, what is this? Usually when they build MOS circuits, there's a parallel, they're called anti-parallel diode to go with it. You see, that diode is going to prevent current to flow from this direction. But current can flow that direction. Even if MOSFET is off, like the main body is off, current can still flow through the diode. So that is a problem with a lot of MOSFETs. They have body diode. Sometimes we have body diode. It's like the PN junctions, like different, like between like here and here, there's a PN junction. Between here, and there's a PN junction. So you can plot quite a few diodes, like in a device, like this is, and here. And even here, you have diode. So you have a lot of diodes. Some of them call this body diodes. So we have to be careful with the body diodes because they actually can flow current in one direction, even the MOSFET is off. So if we sometimes use this as a switch, we have to use two of them back to back. So let's see. Okay, maybe I can use this space. So sometimes if you want to conduct the current, so, Current can go this way, can go this way, yeah. So current will flow from be this way. We can use two MOSFETs, let's see. So we can current can this way. This diode will be actually wrong. So we'll have to flow this way. Yeah.
What's the difference between the two symbols you just drew? Like arrow coming out the bottom versus arrow going in the top?
Going to the top is a PMOS. Out of the bottom is NMOS.
It doesn't come in and then out the bottom?
It does, but it's just how this is defined.
Okay.
It's,
Yeah.
I assume it means because with PMOS, you can ground that one to activate it. So it's
Yeah.
like whether we want a positive voltage or a negative voltage from the side.
Right. That's true too. That's true too. So again, so for MOSFET, I think let's see. I think what I have section 5.2. Yeah. So those are the symbols. You know, this is how we're gonna talk about this later next week a little bit more, like how to use these equations, and we really go through some of the stuff. But I think it's gonna be too much today, so we're gonna stop here. And yeah, just remind you that next week for 2 weeks, you guys be listening online. Okay. The homeworks are posted, so you guys can start it, you know, with the homework. And chapter 5, the only way to get good is just to
Do
a lot of them. Yeah. A lot
Wow,
of
it's gonna be on the 12, you on the 12th, right?
Yeah.
all the piece spice.
Yeah.
think.
If we have questions about the lab, should we reach out to you?
Reach out to the TA.
Yeah.
Okay. Good. See you guys next time.
Too many things that have to.